Welcome back to Mechanical Engineering Made Simple. Today, we are taking a massive stack of reference material. We're looking at the core engineering handbooks covering mechanical vibration, condition monitoring, and shock testing. And we're using all of that to guide you through a highly immersive, high-stakes story.
Right, because we're not just going to sit here and talk about equations and theories today. We're putting you right in the middle of a massive mechanical engineering crisis.
Exactly. You are the lead troubleshooter. You're the top-tier mechanical engineer who has just been called in on an emergency basis to save a critical manufacturing plant from what looks like a completely catastrophic failure.
And, the theoretical material we are unpacking today is incredibly dense. I mean, we are talking about the physics of mechanical impedance, the intricacies of fast Fourier transforms, the brutality of structural fatigue.
It's heavy stuff.
It is, yeah. But engineering knowledge is essentially useless until it is applied to the real world. So we're going to apply it. We are going to walk through the exact methodical process of diagnosing an invisible enemy and engineering a permanent solution.
So picture this scenario. You have just pulled into the parking lot of a massive industrial facility. The plant manager is waiting for you at the loading dock, and he looks completely frantic.
Sweating bullets, I'm sure.
Oh, absolutely. You throw on your hard hat, you put in your ear protection, and you follow him out onto the main factory floor. Instantly, you feel the problem before you even see it. It is vibrating right through the soles of your work boots.
That low-frequency rumble that just travels through everything.
Yeah. He leads you over to a brand new 2,500-pound motor-driven air compressor system. And this thing is violently shaking. I mean, it looks like it is trying to rip itself out of the concrete. It is making an absolutely deafening racket.
And at that weight, the forces involved are terrifying.
Right. And the plant manager is yelling over the noise, telling you that it is burning out its bearings on a weekly basis. But the real disaster is actually across the room.
The transmission path.
Exactly. The vibrations from this compressor are traveling through the concrete slab of the factory and disrupting a row of delicate, multi-million-dollar CNC machine tools.
Which rely on microscopic tolerances.
Right. So they are having to scrap incredibly expensive precision aerospace parts just because this compressor is throwing off their tooling. They are bleeding money by the hour.
It is a terrifying scenario for a plant manager, but for an engineer, it's a puzzle waiting to be solved. To the untrained eye, that compressor is just a blur of chaotic motion and noise.
It's a giant rattling box of metal.
Right. But every vibration tells a story. Equipped with the right analytical tools and a solid grasp of the underlying physics, that machine is going to literally tell you exactly what is failing inside of it.
So our mission for this deep dive is to walk through the process of reading those clues, diagnosing the complex root causes, and applying the core principles of shock and vibration control to fix it permanently.
Yes. And when you walk onto that floor, you know you are not dealing with a clean textbook sine wave. Real life doesn't look like a textbook. You are dealing with a chaotic, complex, harmonic nightmare.
So where do you even begin? I imagine the instinct for a lot of mechanics is to just, grab a wrench, shut the thing down, and start unbolting heavy metal until they find something broken.
Which is the absolute worst thing you could do. You never start with a wrench. Arbitrary intervention is one of the most risky and expensive things you could do in heavy industry.
Why is that?
Well, the handbooks heavily emphasize the philosophy of condition monitoring. This is the practice of measuring specific parameters like vibration, bearing temperature, or analyzing oil debris to predict faults and avoid unnecessary teardowns.
Because every time you tear it apart, you risk messing something else up.
Exactly. Every time you open up a complex piece of heavy machinery, you introduce the risk of creating new faults. You might introduce contamination into the lubrication, torque a bolt incorrectly, or damage a delicate seal.
So by capturing the vibration signature while it is running, you are basically letting the machine's internal physics give you a diagnostic X-ray of its mechanical health.
Yes, that's a great way to put it. You let the machine speak to you first.
Okay, so your first move is just observation. You do a visual walk-around. You note that the compressor and the motor are mounted on a single common steel base plate, but you spot a crucial detail right away.
The weight distribution.
Right. The weight is completely unequally distributed. The static load on the mounts at the heavy engine end is 750 pounds each. But down at the compressor end, it is only 500 pounds per mount.
That uneven weight distribution seems like a massive clue to file away for later. It is going to be incredibly important when we get to the isolation phase.
But right now, you need data. You pull out your transducer kit. Walk me through the actual physical process of capturing this violent shaking.
Well, you have to make a very careful choice about your instrumentation here. You are trying to turn physical, mechanical shaking into a clean electrical signal that a computer can read.
Yeah.
And you generally have a choice between velocity pickups and accelerometers.
And what's the difference in practical terms?
Velocity pickups are transducers that convert the input mechanical velocity into a proportional electrical output. They are robust, they handle high temperatures well, and they are excellent for general machinery vibration, especially at those mid-range frequencies.
But a velocity pickup might miss the microscopic high-frequency stuff happening inside the bearings, right? So you would probably reach for an accelerometer.
You would, yes. You reach for an accelerometer, which measures acceleration and is highly sensitive to high-frequency forces. But you must be extremely careful when you deploy them.
Because of resonance.
Exactly. Accelerometers are essentially tiny masses mounted on piezoelectric crystals. Because they are physical mechanical structures themselves, they have their own internal, natural resonant frequency.
So if the high-frequency shocks from the failing machine happen to hit that internal resonance of the sensor itself,
The accelerometer will literally ring like a bell. It will physically amplify the vibration internally and produce a massive, artificially exaggerated electrical output.
and that overloads your recording equipment.
It does. It exceeds the dynamic range of your data acquisition system, causing the signal to clip. The tops and bottoms of the electrical waveform are just chopped right off.
And once your data is clipped, it's garbage.
Mathematically useless. The harmonic content is completely ruined. So to prevent this, you might have to employ mechanically isolated accelerometers.
How do those work?
They act as a mechanical low-pass filter. They protect the sensing element from those ultra-high transient frequencies, ensuring your actual data remains pristine. Furthermore, how you mount that sensor is critical.
You can't just press it against the metal with your thumb, right?
Absolutely not. Your hand acts as a damper. And you really shouldn't use a flimsy magnetic base if you were looking for ultra-high frequencies either. You often have to drill and tap the machine casing and stud mount the accelerometer directly to the steel.
Or use specialized rigid adhesives.
Right, ensuring there is zero mechanical play between the machine and the sensor.
Okay, so you have your accelerometers perfectly stud-mounted, you route your cables carefully, avoiding any loose wires that might whip around and introduce noise. You record the data, you pack up your sensors, step away from the deafening noise, and you open your laptop.
Now the real analysis starts.
Right, you plug your data into a fast Fourier transform analyzer, an FFT analyzer. And this is where the detective work begins. Because we initially have this messy, chaotic squiggle of a waveform on the screen representing the time domain. How does the FFT actually help us read this?
Well, the time domain waveform of a failing machine looks like a scribbled mess. It is a complex vibration with no clear periodicity. It is all the different vibrations, the spinning shaft, the meshing gears, the vibrating base plate, the floor resonance, all stacked on top of each other.
It's just a wall of noise.
Exactly.
Yep.
The fast Fourier transform is a powerful mathematical algorithm that transforms that messy time domain signal into the frequency domain. It takes the complex wave and breaks it down into its individual sinusoidal components.
It essentially unbakes the cake.
Unbakes the cake, yes. Showing you a neat bar chart of exactly which specific frequencies are present and how much energy is behind each one.
So I'm looking at this FFT plot on the screen, and clue number one jumps out immediately. There are massive, towering vibration peaks. I see a huge spike right at the exact rotational speed of the motor shaft.
Let's say it's an 1800 RPM motor.
Right, so 1800 revolutions per minute. There is a massive spike at exactly 30 hertz, which is 1 times the running speed. My immediate thought is that something is heavy on one side, like an unbalanced ceiling fan throwing its weight around. Is that what we were looking at?
An unbalance would certainly give you a strong peak at 1 times the running speed, or 1 times RPM. If the rotor has a heavy spot, centrifugal force will pull it outward once per revolution. But you have to look closer at the spectrum. Do you see the other massive peak?
Yes, there's another huge peak at exactly double the running speed. The 2 times RPM peak, it's sitting at 60 hertz.
A strong 1 times and 2 times RPM signature is the textbook signature of shaft misalignment. This is incredibly common in heavy industry.
Because you have a massive electric motor coupled to a massive air compressor.
Exactly. The motor shaft and the compressor shaft are supposed to be perfectly collinear. They should be sharing the exact same center line of rotation. But they are not. They're slightly offset or hitting each other at an angle.
So every single time that shaft does a full rotation, The heavy steel coupling connecting them has to physically bend and flex to accommodate that crooked angle.
Right. And because of the geometry of the coupling, it often binds and releases twice per revolution.
Yep.
Hence, the massive peak at 2 times the running speed.
That makes total sense.
And this creates an enormous cyclical bending force. It is trying to snap the thick steel shaft in half thousands of times a minute. This constant heavy pushing and pulling also leads to what we call static eccentricity.
What does that mean physically?
The shaft is literally being forced off-center within its housing, destroying the very clearances meant to keep it spinning freely.
And this perfectly explains why the vibration is so heavy in the axial direction parallel to the shaft. The two machines are essentially shoving each other back and forth through the coupling.
Spot on.
So we have found the primary villain, misalignment. But the plant manager said the machine was screeching and burning out bearings every week. Misalignment explains the heavy thumping, but it doesn't explain the screeching.
No, it doesn't. You need to look deeper.
Right, so I looked deeper into the FFT spectrum for clue number 2. Up in the very high frequencies, there's a broadband increase in noise. It looks like a wash of static, just a little hump on the higher end of the plot.
That is classic high-frequency distress.
But if this is a failing rolling element bearing, how do we actually prove it? The noise from the misalignment is so massive, it feels like trying to hear a pin drop at a heavy metal concert.
That is the exact challenge of signal processing right there.
Yeah.
A failing rolling element bearing generates microscopic high-frequency impacts. Imagine a tiny crack or a pit on the outer race of the bearing.
Like a pothole on a highway.
Exactly. Every time one of the steel balls rolls over that microscopic pothole, it creates a tiny impact. But those impacts contain very little total energy compared to the massive, low-frequency thumping of the misaligned shaft.
So the FFT alone just gets overwhelmed.
The FFT alone often cannot separate that tiny impact from the background noise. To find it, you have to use a brilliant mathematical technique called envelope detection.
I am fascinated by envelope detection. Walk me through the actual mechanics of how a software filter can isolate something that microscopic.
Think about what happens when you hit a large brass bell with a tiny metal hammer. You don't actually hear the sound of the hammer itself, right? You hear the bell ringing at its own natural resonant frequency.
Okay.
A machine structure acts the exact same way. Those tiny impacts from the bearing fault act like little hammers. They strike the bearing housing, causing the surrounding metal structure to ring at a very high natural frequency.
So we aren't looking for the impact, we are looking for the ringing.
Precisely. So the first step in envelope detection is to apply a bandpass filter to the raw vibration signal. We mathematically block out all the low-frequency garbage, the shaft rotation, the misalignment thumping, and we isolate a specific high-frequency window where we know the machine structure likes to ring.
So you filter out the heavy metal concert and you only listen to the frequency of the brass bell.
Yes. But the bell isn't ringing constantly. It rings in distinct bursts every time a ball bearing hits the pothole. This is called amplitude modulation.
Okay, so what is the next mathematical step?
The second step is rectification. We take that high-frequency ringing signal, which is swinging rapidly between positive and negative voltage, and we flip all the negative parts to positive. We then smooth it out to trace the outer boundary, the envelope, of those bursts of ringing energy.
You are essentially drawing an outline around the bursts of static.
Exactly. You are turning bursts of high frequency into a single low-frequency wave that matches the repetition rate. Finally, we take that new envelope waveform and run it through a low-frequency FFT analysis. We're no longer looking at the high-frequency ringing itself. We're calculating the exact repetition rate of the bursts.
And when you run this analysis on your laptop,
The envelope spectrum reveals a crystal-clear, distinct peak, and that peak mathematically matches the exact ball-pass frequency of the outer race of the specific bearing model inside that compressor.
that is incredible. Without ever turning a wrench, without even shutting the machine down, you have mathematically proven that there is a microscopic crack on the outer race of that specific bearing.
You have diagnosed a localized fault. The severe misalignment created extreme bending forces, which destroyed the bearing's static clearance, overloading the steel until a fatigue crack formed.
But the mystery is still not over, because as you were recording your data, you noticed clue number 3, and it was terrifying.
The screech.
Yes, suddenly the machine emitted a horrifying, unpredictable screech. The vibration amplitude spiked wildly out of nowhere. It didn't correlate with the specific multiple of the running speed. It wasn't 1 times or 2 times RPM. It was erratic, chaotic, and it shook the concrete so hard your teeth rattled.
I have seen machines do this in the field.
It sounds like they are possessed. It sounds like the metal is literally tearing. What causes that unpredictable spike?
The technical term for this phenomenon is a self-excited vibration, specifically known as dry friction whip. It is one of the most dangerous conditions a piece of rotating machinery can experience because it physically feeds on its own energy.
Walk me through the physics of the whip. How does a misaligned shaft turn into a self-feeding screech?
We have to trace the domino effect of the mechanical failures you have already uncovered. The shaft misalignment created extreme static eccentricity. Those heavy bending forces cracked the bearing race.
Right, the pothole we just found.
As that bearing rapidly breaks down, it loses its tight internal tolerances. The rotating shaft is no longer held perfectly centered in space. It begins to sag or deflect radially.
It drops down.
It drops. Eventually, that loss of clearance becomes so severe that the fast-spinning steel shaft makes physical contact with a stationary, unlubricated surface. It might be a seal, a guide, or the damaged bearing housing itself.
Metal rubbing violently on metal at 1,800 revolutions per minute.
Yes. And when that rotating surface rubs against the stationary surface, it generates intense dry friction. This friction creates a massive tangential force. And physically, that force is normal or perpendicular to the radial deflection of the shaft.
So it pushes it sideways.
That tangential force is the trigger. It violently shoves the shaft sideways in the direction of the rotation. This sudden sideways shove induces a forward whirling motion. The shaft isn't just spinning on its axis anymore. The axis itself is orbiting in a circle inside the housing.
It is whirling around like a lasso.
Like a heavy steel lasso. And because it is whirling, it generates massive centrifugal force. That centrifugal force pulls the spinning shaft even further outward, pressing it significantly harder against the stationary rub point.
Which means more friction.
Harder contact means more friction. More friction generates a much stronger tangential shoving force. A stronger tangential force means a wider, faster whirl, which creates even more centrifugal force.
It is a runaway, self-feeding loop.
It is. The vibration is literally extracting energy from the rotational power of the motor and converting it into violent destructive displacement. It will continue to amplify until the shaft snaps, the housing explodes, or the motor trips out on overload.
So standing there on the factory floor, you have successfully reverse engineered an entire failure cascade using nothing but an accelerometer and some advanced math.
The whole story laid out in the data.
The machine was installed with a severe shaft misalignment. That misalignment created heavy static eccentricity and cyclical bending forces. Those forces pounded the rolling element bearing until it cracked and lost its clearance. The shaft dropped, rubbed against the stator, and triggered a self-excited dry friction whip, causing the unpredictable screeching and massive vibration spikes.
Exactly.
And because the whole 2,500-pound system is bolted rigidly to the floor on poorly distributed mounts, all of this chaotic, destructive energy is transmitting straight into the concrete, ruining the delicate CNC machining operations across the plant.
It is a comprehensive system failure. But because you have used the data to map out the exact sequence of events, you now know precisely how to intervene and prevent it from ever happening again. The diagnosis is complete. Now, the heavy engineering begins.
You take off your detective hat and you put on your engineering hero cape. We move into the solution phase. Step 1. The mechanical realignment. We have to kill the root cause. The center lines of rotation of the massive electric motor and the air compressor must be made perfectly collinear. You can't just loosen the bolts and eyeball this, right?
Not a chance. The tolerances we are talking about are microscopic. First, you have to ensure the foundation is absolutely sound. You check all the foot bolts to eliminate any soft foot conditions.
What exactly is soft foot?
Soft foot happens when the base of the machine is not sitting perfectly flat on the steel base plate. If one corner is floating by even a few thousandths of an inch, tightening that bolt will literally warp the heavy cast iron frame of the motor down to meet the base.
You are stressing the frame before it even turns on.
Right. You have to use precision steel shims under the feet, so the machine sits perfectly relaxed before you even attempt to align the shafts. Then you remove the heavy steel coupling between the motor and compressor to completely mechanically isolate the two shafts.
And then you break out the precision measurement tools. In the old days, they used highly accurate dial indicators, but today, you are likely setting up a laser shaft alignment system.
Oh, lasers are standard now.
You mount laser emitters and detectors on both shafts, you rotate them, and the computer maps the exact three-dimensional offsets in both the horizontal and vertical planes. You are looking for an accuracy of plus or minus 0.001 inches.
1,000th of an inch.
That is incredibly tight.
It is absolutely necessary for machinery of this size running at that speed. But what is truly fascinating about the mechanical alignment protocol is that you cannot simply align the shafts perfectly while the machine is cold and turned off.
But
If you make it mathematically perfect while it is sitting there at room temperature, it will vibrate heavily the moment you turn it on under load. You have to calculate shim corrections to account for thermal distortion.
wait, really? The metal actually changes shape enough to ruin the alignment.
Significantly. When that giant air compressor runs, the friction of the pistons and the massive compression of the gas generate immense heat. The heavy steel housing of the compressor will heat up and physically expand. As the metal expands, the center line of the compressor shaft will actually rise vertically,
Just from thermal expansion.
just from the heat. The electric motor, however, might run much cooler or expand at a completely different rate. Therefore, you have to calculate the exact thermal growth of both machines.
So you intentionally misalign it.
You intentionally misalign the machine slightly when it is cold, perhaps setting the compressor a few thousandths of an inch lower than the motor, so that when it hits its peak operating temperature, it literally grows into perfect collinear alignment.
That is the difference between a mechanic and an engineer right there. Calculating the thermal growth to pre-bias the alignment. Okay, so you calculate your shims, you align the shafts, the misalignment is cured, the bearings are replaced, the root cause is dead.
But your job is not done.
No, because even perfectly aligned, a massive piston-driven air compressor spinning at 1,800 RPM is naturally going to vibrate. It has huge, heavy pistons reciprocating inside of it. It is the nature of the beast. And you still have to protect those multi-million-dollar CNC machines across the floor.
You cannot let any of that baseline vibration travel through the concrete. You need to break the transmission path. You need vibration isolators.
This brings us to step 2. And this is where we delve into the mathematics of mechanical impedance and vibration isolation. The fundamental problem states the operating speed of our motor is 1,800 revolutions per minute.
If we divide that by 60 seconds, we get our fundamental forcing frequency, denoted as F, which is 30 hertz, 30 cycles per second of heavy shaking.
Our goal is to protect the floor. We decide we want to achieve a transmissibility denoted as capital T of 0.2. This means we want our new isolation mounts to physically block 80% of the vibratory force, allowing only 20% to transmit into the concrete floor.
To achieve that specific transmissibility, we have to calculate the required natural frequency of the isolation system we're going to design. We need to find F sub n.
The natural frequency of the mounts?
Yes. The mathematics of transmissibility dictate that to isolate a forcing frequency of 30 hertz and achieve a T of 0.2, our isolator mounts need to have a natural frequency of exactly 12.2 hertz.
I want to pause on that math for a second because the relationship between natural frequency and physical springs is crucial. Once we know our target natural frequency is 12.2 hertz, how do we know which physical springs to order from the catalog? How soft do they actually need to be?
Well, the natural frequency of a spring mass system is directly tied to how much the spring compresses under the static weight of the machine. The formula for the required static deflection, denoted as delta sub st, is a constant, 9.75, divided by the square of the natural frequency, F sub n squared.
Okay, let's run the numbers.
If we take our target natural frequency of 12.2 hertz, square it, and divide 9.75 by that resulting number, we get our answer. The calculation dictates that the mounts must compress by roughly 0.066 inches under the static dead weight of the machine.
But here is where that critical observation from your very first walk-around comes into play. You noted that the weight of the machine is not equally distributed.
It's way heavier on one end.
Right. It is 750 pounds per mount on the electric motor side and only 500 pounds per mount on the compressor side. If you just buy 4 identical springs that compress 0.066 inches under a standard load and you put them under the machine, what happens?
The heavy end of the machine will sink significantly lower than the light end. The entire base plate will tilt. And when the machine tilts, you completely ruin the microscopic laser alignment you just spent hours perfecting.
You basically twist the frame again.
You twist the frame, the pipes connecting to the compressor will be stressed, and the bearings will fail again. This requires a highly careful selection of heavy-duty metal spring isolators.
Yeah.
You have to order springs with different stiffness rates, different spring constants for the front and the rear.
So stiffer springs in the back, softer in the front.
The stiffer springs go under the heavy motor, and the softer springs go under the compressor. You engineer it so that despite the unequal mass, the static deflection is identical across all four corners. The machine floats perfectly level.
That is brilliant. But wait, if you are just using heavy steel coil springs, won't high-frequency noise travel right up the steel coils, like the sound of the bearings or the motor whine?
Yes, it absolutely will. Heavy steel springs have fantastic low-frequency isolation properties, but they possess very little inherent material damping. High-frequency acoustic energy will transmit straight through the continuous steel path of the coil and into the floor.
It's like a solid acoustic bridge.
Exactly. Therefore, you must construct a compound isolator. You combine the steel springs with elastomeric rubber pads in series. The steel springs provide the large static deflection needed for the 12.2 Hz low-frequency isolation, while the elastomer pads break the metal-to-metal contact, providing the dynamic stiffness and high-frequency noise attenuation.
You essentially build a mechanical firewall.
That's a great way to look at it.
So you have the machine perfectly aligned, compensating for thermal growth. You have it floating perfectly level on custom-engineered compound spring and elastomer mounts. You fire the machine up, it runs smoothly, the floor is perfectly still, the CNC machines across the factory are safe.
A total success.
Almost. Because as you stand next to the compressor, you notice a new localized problem. Step 3. The steel baseplate itself, the massive metal platform that the motor and compressor are bolted to, is resonating.
Airborne noise.
Yes, the airborne acoustic noise is incredibly loud. It is vibrating like a giant steel drumhead, radiating noise into the room. You decide you need to apply a damping treatment directly to the baseplate.
The handbooks outline two primary engineering approaches for applying surface damping: free layer damping and constrained layer damping.
Let's start with free layer.
A free layer treatment involves taking a thick, heavy coating of a viscoelastic material, like a specialized rubber or acoustic mastic, and applying it directly to one surface of the vibrating metal panel. When the steel baseplate bends and vibrates, the damping material stuck to it undergoes tension and compression. It stretches and contracts along with the metal.
I see that a lot in automotive applications. Spray-on deadener on the inside of car doors. But what about a constrained layer treatment? How does that work?
Constrained layer damping is significantly more effective for thick, rigid structures like our base plate. It acts like a mechanical sandwich. You apply a much thinner layer of viscoelastic damping material to the steel base plate, but then you cover that rubber layer with a stiff metal backing plate.
So you trap the rubber.
You trap it. Now imagine what happens when the massive steel base plate tries to bend and vibrate. The stiff metal backing plate heavily resists bending. This architectural arrangement forces the thin viscoelastic rubber trapped in the middle to undergo intense shear strain.
It is not just stretching. The top and bottom of the rubber are being violently smeared back and forth in opposite directions.
That's exactly it.
Smearing. But why is smearing the rubber back and forth so much better at killing the noise?
It comes down to the fundamental physics of material damping, specifically dynamic hysteresis. Viscoelastic materials are structurally unique. At a molecular level, they consist of long polymer chains that are tangled together. They exhibit properties of both elastic solids, they bounce back, and viscous fluids, they flow.
Right.
When you force these tangled polymer chains into extreme mechanical shear strain, they rub against each other. This internal molecular friction converts the destructive mechanical vibratory energy directly into heat.
So you are literally turning sound and vibration into low-grade thermal energy.
Precisely. If we look at the physics mathematically, if you plot the mechanical stress versus the mechanical strain of this viscoelastic material during one single cycle of vibration, you see something fascinating.
What does the graph look like?
The loading curve, as you compress the material, does not trace the exact same path as the unloading curve as it relaxes. The lines separate and form a loop on the graph. This is called a stress-strain hysteresis loop. In engineering, the physical area captured inside that loop represents the specific damping energy dissipated per cycle.
So by making the sandwich.
By maximizing the shear strain with a constrained layer metal sandwich, you maximize the area inside that hysteresis loop. You rapidly bleed off the vibrational energy as heat, essentially putting a heavy, deadening hand on the ringing cymbal. The drumhead effect vanishes.
The machine is now humming perfectly. It is aligned, isolated, and acoustically damped. The crisis is over. But as you are packing up your gear, the plant manager pulls you aside. He looks incredibly nervous.
Oh, they always have one more question.
He says, "Listen, I watched this 2,500-pound compressor thrash violently, screeching and shaking for 3 solid weeks before we finally called you. Did the machine sustain permanent structural damage? Is the cast iron frame going to spontaneously snap in half tomorrow?"
That is a very valid fear.
And you have to give him a definitive scientific answer. You cannot just guess. So you turn to step 4, the principles of structural fatigue and Miner's rule.
This is a profound area of mechanical engineering. Miner's rule is a linear damage accumulation model used to calculate cumulative fatigue damage in metals. To understand it, we have to understand the history of fatigue.
It goes back to aviation, doesn't it?
It does. Back in the early days of aviation, with planes like the de Havilland Comet, engineers discovered that metal doesn't just fail when you pull it hard enough to rip it apart. Metal will fail at stresses far below its ultimate yield strength if you apply and remove that stress repeatedly.
Like bending a paperclip back and forth until it snaps?
Exactly like the paperclip. At a microscopic crystalline level, every cycle of significant stress causes tiny slips in the crystal lattice of the steel. These slip bands eventually form microscopic cracks, which grow with every subsequent bend until the remaining solid metal can no longer hold the load, and it catastrophically shears.
So the metal remembers every bend.
It does. Miner's concept is that every single cycle of stress inflicts a tiny, irreversible fraction of damage to the metal's total lifespan. The equation is elegant, but devastating. The sum of lowercase n sub I divided by uppercase n sub I equals 1.
Let's break those variables down with the plant manager. How do we use that equation to prove his compressor frame won't snap?
Lowercase n sub I represents the actual number of cycles the machine experienced at a specific high-stress level during its failing period. It ran for 3 weeks at 1,800 RPM while misaligned, so you can calculate the exact millions of cyclical bending moments the frame endured.
And uppercase N.
Uppercase n sub I represents the total number of cycles it would take to cause complete failure at that same stress level. You find uppercase n by looking at empirical fatigue curves, often called SN curves, for the specific grade of steel used in the compressor frame.
So you calculate the ratio, the applied cycles divided by the total cycles to failure.
Right. If it endured 1 million cycles at a stress level that takes 10 million cycles to cause failure, it has consumed 1/10 of its life at that stress. You calculate this ratio for every different stress level the machine endured during its thrashing phase, and you sum all those fractions together.
And the critical threshold.
If the total sum equals 1.0, failure is imminent. The structure has exhausted its fatigue life. It will crack. So you sit down with your vibration data, you estimate the bending stresses, you look up the cast iron's SN curve, and you run Miner's rule.
Let's say the total sum comes out to 0.15.
Then you can confidently turn to the plant manager and report that the frame has permanently consumed 15% of its total fatigue life. It took a severe beating, yes, and those microscopic slip bands exist. But mathematically, the structure is still sound, and it is perfectly safe to operate for years to come under normal low-stress conditions.
You present this final analysis to the plant manager. He shakes your hand. The compressor is purring softly on its new mount. The factory floor is completely still, and the precision CNC machines across the building are churning out perfect aerospace parts again. You are a hero.
Job well done.
You pack up your FFT analyzer, you drive back to your engineering office, and you sit down at your desk. But your job is not quite done, because word of your legendary troubleshooting operation has spread across the industry, and your inbox is completely flooded with questions from junior engineers who want to know how you did it.
They want the secrets.
They are studying the same reference materials, but they need the real-world context. So let us transition into answering the most frequently asked questions based on the reference material we have been exploring today.
This is an excellent opportunity to clarify some of the most common points of confusion in the field of mechanical vibration, condition monitoring, and structural dynamics.
FAQ number 1 comes from a junior analyst who is staring at an FFT plot. They asked, how do I definitively tell the difference between an unbalanced issue and a misalignment issue in a vibration spectrum? They both seem to happen right at the primary running speed of the machine. We touched on this, but let's dive deeper into the nuances.
It is a critical distinction that trips up a lot of young engineers. Unbalance, where a rotor literally have a heavy spot on one side, typically shows up as a massive solitary peak, heavily concentrated at exactly 1 times the RPM. But crucially, this vibratory force will be absolutely dominant in the radial direction.
That means the machine is shaking violently up and down or side to side, perpendicular to the axis of the shaft.
Correct, because the heavy spot is actively throwing its weight outward centrifugally as it spins. Misalignment, however, creates a complex bending moment across the coupling. As we discussed earlier, it often manifests as strong peaks at 1 times AND, 2 times the RPM.
Depending on the coupling design.
Right, depending on the exact geometry of the coupling, you might even see heavy peaks at 3 times or 4 times the running speed. But the ultimate differentiator is the direction of the force. Misalignment generates disproportionately heavy vibration in the axial direction, parallel to the shaft, as the two misaligned machines aggressively push and pull against each other through the distorted coupling.
But what if the data is just messy? What if you have multiple peaks clustered right around the 1 times RPM mark and you cannot tell what is what? Let's say it's an electric motor and the running speed is really close to the electrical frequency.
That is a very common scenario. To solve it, you must employ zoomed frequency analysis. This is a high-resolution, mathematically intensive digital processing technique that allows you to zoom in on a very narrow slice of the FFT spectrum and massively increase the resolution.
Like putting a magnifying glass on the data.
Exactly. It allows you to separate closely spaced frequency components that would otherwise blur together into a single fat peak. For example, in an AC induction motor, the mechanical rotation harmonic might be sitting at 29.8 Hz due to slip. But the electrical pole-passing frequency driven by the alternating current might be at exactly 30.0 Hz.
Without zoom analysis, they look like one mechanical problem.
With high-resolution zoom analysis, you can see both peaks clearly and definitively diagnose whether you are dealing with a mechanical unbalance or a broken electrical rotor bar.
That is the power of high-resolution data. Moving on to FAQ number 2, which shifts gears a bit into manufacturing. An engineer asks, what exactly is stick slip, and why do my machine tools violently chatter and ruin the surface finish of my precision parts? I hear the term stick slip all the time in relation to friction. What is actually happening?
Stick slip is a fascinating and highly destructive physical phenomenon. The engineering handbooks formally classify it as a relaxation oscillation. To visualize it, imagine a heavy cast iron tool support on a large lathe. This support has to slide smoothly along heavy metal guideways to cut apart.
Okay, I am picturing it.
As the electric drive motor begins to push the support forward, elastic deformation begins to build up in the mechanical drive system. The gears, the lead screws, the mounting brackets, they all begin to physically wind up and stretch under the torque.
It's like winding up a massive, stiff rubber band. The motor is turning, but the heavy tool support hasn't moved yet.
Exactly. The support doesn't move immediately because it is held firmly in place by static friction or resting friction. And the coefficient of static friction between two dry metal surfaces is very high. So the drive system continues to wind up, building immense spring tension.
Waiting to snap.
Eventually, the mechanical spring force of the wound-up drive system exceeds the holding force of the static friction. The tool's support violently breaks free and jumps forward. But the critical moment is right here. The instant the support begins to move, the friction dynamics change. The high static friction instantly drops to the much lower dynamic or sliding friction value.
Because sliding friction is always lower than resting friction, so the resistance suddenly vanishes.
Yes. And because the massive resistance suddenly vanished, the heavy tool support lunges forward rapidly. It overshoots its target, completely unwinds all the pent-up tension in the drive system, and comes to a dead stop.
And then it grabs again.
The moment it stops, the high static friction violently grabs it again. The drive system begins to wind up again, building tension until it breaks free once more. Grab, lunge, stop. Grab, lunge, stop. This entire cycle can repeat hundreds of times a second.
This incredibly rapid, violent stuttering is stick slip. When a sharp cutting tool does this against a spinning piece of aerospace aluminum, it leaves terrible chatter marks, destroys the dimensional tolerances, and ruins the surface finish.
It does.
So how do you cure a relaxation oscillation like that? You can't just tell the machine to stop stuttering.
The cure usually involves fundamentally altering the mechanical dynamics. You can massively increase the structural stiffness of the drive system so it cannot wind up like a rubber band in the first place. Or, more commonly, you use specialized whey lubricants complex oils laced with friction modifiers designed specifically to lower the static friction coefficient, so it is almost identical to the dynamic friction coefficient.
If there is no massive drop in resistance when the machine starts moving, the lunge disappears and the motion becomes perfectly smooth.
That is exactly the goal of a good way lube.
That is a brilliant explanation of resting versus sliding friction. Okay, final FAQ, number 3, diving into the extreme world of shock testing. What is the fundamental difference between a drop table test and a pyroshock test? Both sound like ways to break things on purpose.
They are ways to test survivability, but they represent two completely different extremes of physical shock testing. They test entirely different failure modes. A drop table creates what is known mechanically as a velocity shock.
What does that setup look like?
You take a piece of heavy equipment, strap it securely to a metal table, hoist it high into the air, and drop it freely onto a heavy anvil. It creates a sudden, massive net velocity change. The whole object is moving fast, and then it stops abruptly.
Like a car crash.
Exactly like a car crash. This type of velocity shock has immense damage potential for basic, heavy structural components, particularly at low frequencies. The massive deceleration forces can permanently bend thick steel frames, snap heavy mounting bolts, and tear heavy components right off their mounts.
But a pyroshock test doesn't look like a car crash at all.
Radically different. Pyroshock, or pyrotechnic shock, simulates the violent detonation of an explosive device. This is heavily utilized in the aerospace industry, for example, simulating the explosive bolts used to physically separate rocket stages in space.
So it's an actual explosion.
An explosive charge generates extreme high-frequency, high-magnitude stress waves that ripple aggressively through the solid metal structure. However, unlike the drop table, there is almost no rigid body motion. The object doesn't actually fly across the room. The net velocity change of the overall system is near zero.
If the object doesn't really move, what is actually getting damaged by the explosive shock wave?
A pyroshock is relatively harmless to heavy structural steel frames. They just ring and absorb it. But those intense high-frequency stress waves are absolutely lethal to delicate electronic components. The stress wave traveling through the metal can shatter brittle ceramic microchips, snap microscopic solder joints, and cause relay contacts to violently bounce open and closed.
It shakes the small stuff apart.
Yes. When engineers analyze pyroshock data, they look at a complex graph called the shock response spectrum. They specifically focus on finding the knee frequency, which is the critical point on the graph where the low-frequency slope transitions into the high-frequency plateau of maximum energy. In a pyroshock event, that knee frequency is often sitting between 1,000 and 5,000 hertz. It is incredibly fast, high-energy structural ringing that will shred a circuit board in milliseconds.
Wow. From dropping heavy iron on an anvil to detonating explosives next to a microchip, the fields of shock and vibration truly cover an incredible, vast spectrum of physical extremes. Which brings us to our wrap-up. What an incredible journey today. We walked onto a deafening factory floor with a massive 2,500-pound machine that was literally tearing itself to pieces. We learned how to read its invisible language.
We use the tools of the trade.
We captured the complex harmonic vibration signal, used the FFT to spot the 1 times and 2 times axial peaks proving severe misalignment, and employed the brilliant technique of envelope detection to find the microscopic, high-frequency ringing of a cracked bearing hidden beneath the noise.
And we tracked how that failure cascade led to a terrifying, self-excited, dry friction whip.
Then we applied core engineering principles to solve it permanently. We aligned the shafts to the 1,000th of an inch while compensating for thermal growth. We calculated the exact natural frequency and static deflection required for compound spring and elastomer isolation. We implemented constrained layer damping using the molecular physics of the stress-strain hysteresis loop. And finally, we verified the cast iron frame's survival using the cumulative fatigue mathematics of Miner's rule.
It is a comprehensive demonstration that vibration is not just a nuisance, and it is certainly not a random occurrence. It is a highly structured mathematical language. When engineers take the time to learn to read the vocabulary of frequencies, amplitudes, phase angles, and spectra, they gain a superpower. They can literally look inside solid metal through heavy steel casings and understand precisely what the machinery is experiencing and how to save it.
And before we let you go, our expert has a final, provocative thought to leave you with, building on everything we have covered today.
Consider the trajectory of our field. Today, we solve this massive industrial problem using the traditional, highly refined, tactile arts of mechanical engineering. We used physical steel shims, precision dial indicators, we calculated mechanical static deflections for heavy metal springs, and we applied viscoelastic rubber to dissipate heat.
The old school methods.
But we are rapidly accelerating into a new era. We are seeing the rise of active AI-controlled magnetic bearings and smart structural materials. These modern systems use powerful electromagnets to suspend rotating shafts entirely in midair with zero physical contact. They use advanced computer algorithms to analyze the vibration data and change the magnetic stiffness and damping properties in real time, thousands of times a second. They can actively cancel out forces like severe misalignment or dry friction whip before the vibration even physically manifests in the frame.
A machine that feels its own destructive forces and mathematically heals its own vibrations in milliseconds.
Precisely. So the question I leave you to mull over is this. As these active, self-correcting smart materials and magnetic suspensions become cheaper and become the new industry standard, will the tactile, mechanical arts of physical laser alignment, calculating heavy rudder isolators, and performing manual spectrum analysis become a lost science? Will we forget how to tune the iron? Or will the fundamental physics of the stress-strain hysteresis loop and the brutal reality of structural metal fatigue always require a mechanical master's touch, knowing that software and algorithms can never fully repeal the physical laws of nature?
That is a fantastic, heavy question to leave off on. Are we programming the future of mechanics, or are we just putting a high-speed digital band-aid over raw, undeniable physical forces? We will let you ponder that on your own. If you haven't already, give us a like and follow, and please leave us a comment if you enjoy the podcast. We love to hear from the folks who make this possible.